Welcome to the deep dive.
Hello.
Today, we're tackling, well, a really giant idea in cosmology. It's one that fundamentally changes our picture of the universe's absolute first moments.
Yeah, a big one.
Our mission today is to unpack cosmic inflation.
That's right. And we're diving into a pretty dense source for this.
Yeah.
You should think of like a really comprehensive article, maybe like something you'd find digging deep on Wikipedia, but we're going to crack it open for you.
Exactly. Try and pull out the most important bits.
Yeah, the key insight.
We want to understand why this really mind-bending idea was even proposed in the first place.
And how it might actually work. That's crucial.
And, what does the universe itself tell us about it? What's the evidence? What are the challenges that are still out there?
Right.
So by the end of this deep dive, you should have, hopefully, the essential picture of this concept. It really sits at the heart of modern cosmology.
It really does.
Okay, let's unpack this.
All right. So, cosmic inflation. At its core, the theory proposes that the universe, in its absolute earliest moments, we're talking unimaginably early.
Like fractions of a second.
Tiny, tiny fractions, yeah. It went through this period of incredibly rapid exponential expansion.
Exponential. So not just fast, but acceleratingly fast, like compound interest, but for space itself.
Kind of like that, yeah. But the scale is just, well, it almost defies intuition. Our source mentions distances were literally doubling every tiny fraction of a second. Think like 10 to the minus 37 seconds.
Wow.
And this whole burst, it lasted for at least 10 to the minus 35 seconds. The numbers are just staggering.
It's really hard to get your head around that kind of speed. Is there like an example in the source, something to help grasp the scale?
There is, actually. It gives you a sense of the sheer scale change. Imagine a region of space, maybe just 1 centimeter across before inflation kicked in.
Okay, 1 centimeter.
During that incredibly brief inflationary period, that 1 centimeter could have expanded to be larger than, get this, 20 times the distance from the Earth to the moon.
Whoa. Okay, that is mind-blowing. 1 centimeter to bigger than the Earth-Moon distance, almost instantaneously.
Pretty much. So the entire observable universe, all the stars, all the galaxies we can see, it could have started from something unbelievably small. The source points out that all the mass and energy we see today probably originated from a region that was just incredibly tiny, maybe 4 times 10 to the minus 29 meters across.
That's smaller than anything I can imagine.
And inflation would have blown that tiny speck up to maybe 0.9 meters across. Almost a meter.
Nearly a meter from something subatomic. That's incredible. And you mentioned this helps explain the large-scale structure of the universe. How does that work?
Right. This is really a critical insight of the theory. The idea is that even in that initial tiny microscopic patch, there were these minuscule quantum fluctuations, little jiggles in energy and density.
And quantum weirdness.
Exactly. And inflation didn't just smooth everything perfectly flat. Instead, it took those tiny quantum fluctuations and stretched them out to enormous cosmic sizes.
So they became huge.
Yeah, they became the sort of slight variations in density across the vastness of space. And these variations, magnified by inflation, acted like gravitational seeds.
Seeds?
Yeah. Seeds around which matter, billions of years later, started to clump together due to gravity. That's how we think galaxies and clusters of galaxies and all the big structures we see got started.
So inflation didn't just make space huge, it imprinted the initial blueprint for everything that came later.
That's a great way to put it. It imprinted the initial texture. And it's really important to distinguish this early inflation from the expansion happening today.
Right. The universe is still expanding now.
It is. But after inflation stopped, the expansion slowed down dramatically. It continued, but at a much more leisurely pace for billions of years. It was only much, much later, the source says, after about 7.7 billion years had passed, so roughly 5.4 billion years ago, that the expansion started to speed up again.
And that's the acceleration we attribute to dark energy, right?
Exactly. So you have 2 periods of accelerated expansion, but they're very different beasts.
How so?
Well, inflation was driven by these incredibly high energy densities in the very early universe associated with this inflatant field we'll talk about. Dark energy, on the other hand, is this much, much weaker effect. It only started dominating the expansion rate when the universe was already vast and much older.
So mathematically similar maybe, but physically totally different scales and causes.
Precisely. Different physics, different eras.
Okay, so inflation is this radical idea, super fast, early expansion that seeds cosmic structure. But why? Why did physicists feel the need to invent something that sounds so, well, extreme? What was wrong with the standard Big Bang model?
That's the key question, really. Inflation wasn't just pulled out of thin air. It was specifically developed back in the late 70s and early 80s to solve some really quite serious puzzles in the standard Big Bang picture.
Puzzles? Like what?
Like problems that made it seem the universe needed these incredibly special, almost miraculously finely tuned initial conditions just to end up looking the way it does today.
Oh.
Inflation offered a natural way for the universe to arrive at those conditions without needing that initial perfection.
Okay, lay out the first big problem for us. What was puzzle number one?
The first one was the magnetic monopole problem.
Magnetic monopoles. Hang on, aren't magnets supposed to have two poles, a north and a south?
They are in our everyday experience. But these theories that try to unify the fundamental forces, they're called grand unified theories, or GUTs, they predicted that at the super high temperatures of the very early universe, you should have produced these particles with only one magnetic pole, just a north or just a south.
Okay, weird particles, and they should still be around.
According to the GUTs, yes, they should be very heavy, very stable, and produced in huge numbers. They should basically be everywhere, maybe even the main component of the universe's mass.
But we don't see them.
We absolutely do not. Physicists have looked really hard, and the experiments place incredibly strict limits on how many could possibly be out there. It's way, way lower than the simplest GUTs predicted. This was a big headache.
So how does inflation make these hypothetical particles vanish?
It's actually quite elegant. The idea is if inflation happened after the universe cooled down just a tiny bit below the temperature where these monopoles would be readily produced, then even if a few monopoles did form before inflation started, the absolutely immense exponential stretching of space would dilute them. It would spread them out so incredibly far apart that the chance of finding one in our observable part of the universe becomes practically zero.
It just spreads them too thin to see.
Exactly. Dilutes them to undetectable levels.
It does feel a bit like explaining the absence of something we weren't even sure existed. I think the source had a quote about that skepticism.
It did, yeah. It quotes Martin Rees, who pointed out something like, skeptics about exotic physics might not be hugely impressed by a theoretical argument to explain the absence of particles that are themselves only hypothetical.
Which seems fair enough, if that was the only thing inflation explained.
Right, but it wasn't. That's the key. It tackled other major problems, too.
Okay, what's the next big puzzle inflation addresses?
Problem number 2, the flatness problem.
Flatness? You mean like the universe isn't curved?
On the largest scales, yes. Its overall geometry seems to be very, very close to Euclidean geometry. You know, the kind you learn in school where parallel lines stay parallel. It's not positively curved like the surface of a sphere or negatively curved like a saddle shape. It's flat.
And we know this from observations, like the cosmic microwave background.
Exactly. Observations of the CMB, especially by the Planck satellite, have pinned it down incredibly precisely. The universe is flat to within about 0.5%. Remarkable flatness.
Okay, so what's the problem with that? Why is being flat a problem?
The problem arises in the standard Big Bang model without inflation. As the universe expands, any initial curvature it might have started with gets diluted away. But, and this is the crucial bit, curvature dilutes much more slowly than the density of matter or radiation.
Okay.
So for the universe to be this incredibly flat today, after 13.8 billion years of expansion, it must have started out fantastically flat right near the Big Bang. The deviation from perfect flatness back then would have had to be, like, exponentially small. Smaller than 1 part in 10 to the power of 60 or something crazy like that.
That sounds like unbelievable fine-tuning, like balancing a pencil on its point for billions of years.
That's exactly the analogy often used. It seems like an unstable situation that requires an absurdly precise initial setup. Inflation offers a dynamic solution. The exponential expansion during inflation acts like stretching that pencil. Or more accurately, like stretching a crumpled ball of paper or a wrinkled rubber sheet. As you stretch it exponentially in all directions, any initial wrinkles or curves just get ironed out. Inflation naturally drives the geometry towards flatness, regardless of how curved it might have been initially.
So it forces the universe to become flat.
Pretty much.
Yeah.
Makes flatness the natural outcome, not a finely tuned accident.
Okay, so no monopoles and a naturally flat universe. That's 2 big wins. What's the third major puzzle? The horizon problem. This one always feels the trickiest to me.
It is quite counterintuitive. Let's start with the cosmological horizon. That's basically the edge of the observable universe for us. It's the maximum distance light has had time to travel to reach us since the universe began.
So stuff beyond that horizon we can't see, and it can't have affected us yet.
Right. Regions beyond our horizon are, in a sense, causally disconnected from us. They haven't had time to exchange signals or influence each other. Now, here's the problem. When we look at the cosmic microwave background radiation, that afterglow of the Big Bang, it's coming to us from all directions.
The heat left over from the early universe.
Exactly. And it's incredibly uniform in temperature. But when we look at 2 points on the CMB map that are on opposite sides of the sky, in the standard Big Bang model without inflation, those two regions were actually much farther apart back when the CMB light was emitted than light could have traveled between them. They were outside each other's horizons. They should have never been in causal contact.
So they couldn't have talked to each other.
Correct. Yet they have almost exactly the same temperature to within 1 part in 100,000. How did they know to be the same temperature if they could never interact or exchange heat or information?
That is weird. It's like finding two strangers in opposite corners of a huge dark room who somehow ended up wearing the exact same temperature thermostat setting.
That's a good way to think about it. It looks like another incredible coincidence requiring fine-tuning. Inflation solves this beautifully.
How does it do that?
Inflation proposes that before inflation kicked in, the entire region that would eventually become our observable universe was actually incredibly tiny, so small that it was all causally connected. Everything within that tiny patch could interact and reach thermal equilibrium. It was a small, uniform region.
Ah, so they started out together knowing the same temperature.
Exactly. Then inflation happened. Boom! It expanded that tiny uniform patch so rapidly and by such an enormous factor that regions which were once close neighbors got flung vastly far apart, pushed way outside each other's horizons.
So inflation separated them?
Yes. But because they started from the same uniform, causally connected state, they retained that uniformity. Even though they spent billions of years causally disconnected, when those regions eventually expanded back into our observable horizon much later, we see them having the same properties, the same temperature, because they originated from that common uniform starting point.
So inflation sets up the initial uniformity, then blows it up to cosmic scale.
You got it. The source mentions this idea of de Sitter space, where the horizon kind of stays put while space expands exponentially under it, constantly pushing things beyond the horizon, which naturally leads to homogeneity within any patch that gets inflated.
Okay, that really ties it together. Monopoles diluted, flatness enforced, and horizons explained by starting small and uniform before blowing up. These are really elegant solutions to what seemed like big problems.
They really are. It's why the idea gained traction so quickly.
But let's get into the how. I mean, what kind of physics could actually drive this insane exponential expansion? What's the engine?
That's where things get a bit more speculative, because the exact physics isn't fully pinned down. But the leading theoretical idea involves a hypothetical new field, a type of energy field permeating space, usually called the inflaton field.
The inflaton. So a new fundamental field just for this job.
That's the prevailing thought, yes. The concept is that this inflaton field started out in a very high energy state, sometimes called a false vacuum state. It's like being perched high up on a potential energy hill, but in a sort of stable or semi-stable way, at least for a short time.
Okay, high energy. How does that drive expansion?
This is where general relativity comes in. In this high energy false vacuum state, the inflaton field has a peculiar property. It exerts a negative pressure.
Negative pressure, that sounds like suction, not pushing things apart.
It does sound counterintuitive. But in Einstein's theory of gravity, energy, and pressure, both contribute to space-time curvature. And it turns out that a strong negative pressure acts as a source of gravitational repulsion. It makes space want to fly apart.
Okay. Gravity becomes repulsive.
In effect, yes. This negative pressure associated with the inflaton field's potential energy creates this outward gravitational push, driving space to expand exponentially. The energy stored in the inflaton field itself is enormous, and it's this energy that powers the whole inflationary epoch.
And where did all the stuff we see today, particles, radiation, heat, where did that come from? Did inflation create it?
Not directly during the expansion phase. That phase is actually a period of supercooling. As space expands so rapidly, the temperature drops dramatically. The creation of matter and energy happens right at the end of inflation in a process called reheating.
Reheating.
Yeah. When the inflaton field finally rolls down off its high-energy perch and settles into its true minimum energy state, the true vacuum, inflation stops. The huge amount of potential energy stored in the field gets released. It decays, basically, transforming into a hot, dense soup of standard model particles, quarks, electrons, photons, everything.
So the inflaton dumps its energy into creating the hot Big Bang.
Exactly. Reheating is the transition phase. It marks the end of inflation and the beginning of a hot, radiation-dominated era that we traditionally think of as the standard Big Bang. The energy of the inflaton essentially becomes the initial energy budget for the rest of cosmic history.
Okay, so the inflaton field drives expansion via negative pressure and then decays via reheating to create the hot early universe. What are the sort of main effects or consequences of this whole process?
Well, we've touched on the big ones.
Yeah.
First, obviously, the enormous space expansion itself. Stretching space, pushing things apart, solving the horizon problem by starting from a small causal patch.
Right, making the universe huge and connecting distant regions' origins.
Second is the smoothing effect. This rapid, accelerating expansion is incredibly effective at ironing out almost any pre-existing irregularities. Any initial variations in density, temperature, spatial curvature, weird anisotropies, they all get stretched and diluted away to almost nothing.
Like the flatness thing, but for everything else, too?
Pretty much. The source compares it to the no-hair theorem for black holes, which says black holes are defined only by mass, charge, and spin. All the details are lost. Inflation, similarly, erases almost all initial complexity, leaving the universe in a very simple, smooth, symmetric state, dominated just by the inflaton's energy.
So it makes the universe incredibly uniform by the time it ends.
Exactly. Very flat, very symmetric, mostly empty, except for the inflaton field itself, except for those tiny quantum fluctuations in the inflaton field we talked about earlier. Those are the crucial exception. They don't get completely smoothed away, they get stretched.
The seeds of structure.
The seeds of structure. And then the third major effect is reheating. As we just discussed, this is where the cold expansion ends. The inflaton decays, and its energy gets converted into thermal energy, creating the hot particle soup that starts the standard Big Bang evolution. The temperature shoots back up, maybe even close to the pre-inflationary level.
And the source mentioned we don't fully understand how reheating works.
The precise mechanism is still an area of active research, yeah. It could be quite complex, possibly involving things like particles being produced resonantly as the inflaton field oscillates around its minimum. But the overall picture inflaton energy converting to particles is the key idea.
It's amazing how this one concept, this inflaton field doing its thing, seems to accomplish so much. Let's shift gears slightly and look at the history. How did this idea come about? Who were the key players?
Well, like many big ideas, it built on earlier work. People like Einstein with his cosmological constant, Willem de Sitter exploring exponentially expanding universes way back. There were others who noted issues like the horizon problem or studied vacuum energy.
But the modern idea of inflation,
it really started to crystallize in the late 1970s. Alexei Starobinsky, working in the Soviet Union in 1979, proposed a model based on quantum corrections to gravity, which effectively led to a period of exponential expansion, a de Sitter phase.
Okay, so Starobinsky had an early version. Then Alan Guth, he seems to get a lot of the credit.
He does, especially for popularizing the idea and coining the name inflation. Guth, over in the U.S., was independently motivated, largely by that magnetic monocle problem we discussed. Around 1979-1980, he proposed that the universe could get trapped in a high-energy, false vacuum state and then tunnel out, driving exponential expansion in the process. His big paper came out in 1981.
And others were thinking along similar lines, too.
Yes. Around the same time, Katsuhiko Sato in Japan and Demosthenes Kazanes in the U.S. were also exploring exponential expansion ideas to solve cosmological puzzles like the horizon problem or issues with domain walls. It was clearly an idea whose time had sort of come.
But Guth's initial version, the one with the bubbles tunneling out, that had a problem, right? You mentioned it earlier, the graceful exit problem.
Exactly. His original model, often called old inflation, relied on these bubbles of true vacuum forming within the false vacuum. But for inflation to solve the other problems, it had to last long enough, which meant the bubbles formed relatively slowly. The exponential expansion would then stretch the space between the bubbles so fast that they'd never collide.
And collisions were needed for reheating.
Right. You needed the energy released in bubble collisions to fill the universe uniformly with heat and particles. Without enough collisions, you'd end up with a very empty, cold, and lumpy universe, not like ours. It wasn't a graceful exit from inflation.
So how did they fix that? Who solved the graceful exit problem?
That breakthrough came quickly in 1982. Andrei Linde, also then in the Soviet Union, and independently Andreas Albrecht and Paul Steinhardt in the U.S., proposed what's now called new inflation, or more commonly, slow roll inflation.
Slow roll. That sounds like the inflaton field we talked about.
Precisely. Instead of tunneling bubbles, their idea was that the inflaton field wasn't trapped, but was slowly rolling down a very flat part of its potential energy hill, like a ball rolling very slowly down a gentle slope.
And that slow roll causes inflation.
Yes. As long as the field is rolling slowly on that flat part, you get inflation. But crucially, the potential eventually gets steeper. When the field reaches that steeper part, it rolls down faster, oscillates around the bottom, and decays, reheating the universe smoothly and uniformly everywhere within a given inflating patch.
Ah, so the slow roll provides both the inflation and the graceful exit.
Exactly. It was a much more elegant and workable mechanism.
And was it around this time that the connection to structure formation, those quantum fluctuations, became clear?
Yes, that was another absolutely crucial piece of the puzzle happening in parallel. The realization that the unavoidable quantum jiggles in the inflaton field itself during the slow roll would be stretched to macroscopic scales, creating the tiny density variations needed to seed galaxies. That was huge.
Who figured that out?
It was worked out by several groups around 1981-1982. Vyacheslav Mukhanov and G.V. Chibisov calculated it for Starobinsky's model. Then Stephen Hawking, Starobinsky himself again, Guth and So-Young Pai, and James Bardeen, Paul Spanhart, and Michael Turner all independently derived similar results for the slow roll models.
So many key people involved.
It was a very exciting time. This connection to structure formation elevated inflation from just solving old problems to actually predicting something fundamental about the large-scale structure we observe. That made it much more compelling.
Okay, so the theory evolved from solving problems, got a working mechanism with slow roll, and then gained this incredible predictive power for cosmic structure. That's a powerful narrative. How does it stand up today when we actually look at the universe? What's the observational status?
This is really where inflation has had its biggest successes. It makes very specific, testable predictions about the cosmos.
And have those predictions been confirmed?
Several of the key ones have been confirmed with remarkable precision. First, the overall homogeneity and isotropy of the universe. The fact that it looks basically the same in all directions on large scales, that's exactly what you'd expect if our observable patch came from one tiny, uniform, pre-inflationary region. The CMB confirms this smoothness to incredible accuracy.
Okay, uniformity checked. What else?
The flatness. As we discussed, inflation strongly predicts the universe should be spatially flat. And the measurements, especially from the Planck satellite analyzing the CMB, show it is flat to within about 0.5%. That's a major triumph for inflation.
Flatness checked. And the monopoles?
Well, their absence is perfectly consistent with inflation having occurred and diluted them away, so absence checked, you could say.
All right, those are the big qualitative predictions. What about the structure formation part, the prediction about the seeds?
This is where the most stringent quantitative tests have come from. Inflation predicts that those primordial density fluctuations, the seeds of galaxies, weren't just random noise. They should have very specific statistical properties. They should form what's called a nearly scale-invariant Gaussian random field.
Okay, that's a mouthful. Nearly scale-invariant Gaussian random field. What does that actually mean for observations? How do we test that?
Basically, Gaussian means the fluctuations follow a specific statistical distribution, like a bell curve. Scale invariant means the amplitude of the fluctuations is almost the same on all different physical size scales, small scales, medium scales, large scales. Nearly means it's not perfectly the same, but deviates slightly in a predictable way.
How predictable?
The deviation from perfect scale invariance is described by a number called the spectral index, usually written NS. Perfect scale invariance would be NS equals 1. Simple, common models of slow roll inflation predict energies to be slightly less than 1, typically somewhere between 0.92 and 0.98.
Okay, a specific numerical prediction.
Yes. And there's another key prediction related to gravitational waves. Inflation should have also generated ripples in space-time itself, primordial gravitational waves. The strength of these waves relative to the density fluctuations is measured by another number, the tensor to scalar ratio, R. Simple models often predicted R might be around 0.1 or perhaps a bit larger.
So specific predictions for N's and R. What did the big CMB experiments like COBE, WMAP, and especially Planck find when they mapped the tiny temperature differences in the CMB?
This was the crucial test. First, they confirmed that the fluctuations do look Gaussian, as predicted. That was a big check mark. Then they measured the spectral index, NS.
And the result?
The Planck satellite data, the most precise we have, gives NS as 0.968, Dani 0.006.
Wait, 0.968. That's right, smack in the middle of the 0.92 to 0.98 range predicted by the simple models?
Exactly. It's slightly less than 1, just as predicted. This measurement is widely considered one of the most important pieces of observational evidence supporting the basic inflationary picture. It's a stunning confirmation.
Wow. What about the gravitational waves, the ratio R?
There, the results have been more about setting limits. Planck data, combined with other ground-based experiments, has shown that R must be less than about 0.11. And more recent analyses push that limit down further, maybe R.06 or even lower.
So no definitive detection of primordial gravitational waves yet?
Not yet. This rules out some of the very simplest inflation models that predicted a larger R, but it's still consistent with many other well-motivated models. Finding those gravitational waves is kind of the next smoking gun people are searching for.
The agreement seems really impressive, especially for N's. Are there any observational wrinkles, anything that doesn't quite fit the simplest inflationary picture?
There are a few things, often called anomalies, in the CMB data that some people point to. They aren't statistically overwhelming, but they're curious. For example, the fluctuations on the very largest angular scales in the sky, the quadrupole and octupole, seem to have a slightly lower amplitude than predicted by the simplest models.
Lower than expected.
Yeah. And there have also been claims of some strange alignments, like these largest scale patterns seeming to align with the plane of our own solar system, the ecliptic.
That sounds suspicious. Could that just be contamination from our galaxy or something?
That's one possibility. Or it could just be a statistical fluke in any random data set. You can sometimes find weird-looking patterns just by chance. Others wonder if it might hint at more complex physics during inflation, or maybe even problems with the basic model. The interpretation is really debated. They're interesting puzzles, but not necessarily deal breakers for inflation yet.
Okay. And the next big observational push is for those gravitational waves.
Absolutely. The main target is detecting a specific type of polarization pattern in the CMB called B-modes. Primordial gravitational waves generated during inflation are predicted to leave a faint but characteristic B-mode signature.
So if we see those B-modes,
detecting them and measuring their strength, which tells us R, would be incredibly powerful evidence. It would not only confirm a key prediction, but also tell us the actual energy scale at which inflation happened. Simple models place this scale incredibly high, maybe around 2015 to 1016 GeV, close to the GT scale.
I remember a few years back, there was a huge buzz about an experiment called BICEA P2 detecting these B modes. What happened with that?
Right. There was enormous excitement in 2014 when the BICEA A2 team announced a detection. However, further analysis, especially incorporating data from Planck, showed that much, or perhaps all, of the signal they saw was likely due to polarized dust emission within our own Milky Way galaxy, which unfortunately can mimic the B-mode pattern.
Ah, so it wasn't the primordial signal after all.
It seems not, or at least not clearly. So the hunt continues with more sensitive experiments and better ways to subtract foreground contamination. The current limits on R are significantly tighter now because of that work, pushing down below R equals 0.06.
So observationally, inflation scores very high marks on homogeneity, flatness, and the spectral index ends. The search for gravitational waves is ongoing, and there are a few minor anomalies being debated. What about the theory itself? Does inflation have theoretical problems or challenges?
Oh, absolutely. Despite its observational successes, inflation is far from theoretically complete or problem-free. It faces some pretty significant conceptual challenges, and there's a lot of ongoing debate within the theoretical physics community.
Okay, like what? What's a major theoretical hurdle?
Well, one big one comes back to this idea of fine-tuning, but this time within the inflationary model itself. Remember how we needed that inflaton field to roll slowly down a flat potential?
Yeah, the slow roll condition.
Getting that to happen typically requires the shape of the inflaton's potential energy curve to be exquisitely flat. And the mass, or couplings, of the inflaton particle often need to be incredibly small compared to what you might naturally expect. It looks like you might need to fine-tune the parameters of the inflaton theory itself to get inflation to work properly, to last long enough, produce the right kind of fluctuations, and end gracefully.
So, wait, didn't inflation supposedly solve fine-tuning problems like flatness and horizon? Now you're saying inflation itself might need fine-tuning.
That's exactly the criticism. Some argue that inflation doesn't eliminate fine-tuning, it just shifts the problem from the initial conditions of the universe to the initial conditions and properties of the inflaton field. It's a very active area of research trying to build models where slow-roll inflation happens more naturally without this apparent fine-tuning. Some ideas involve specific symmetries or embedding inflation within larger frameworks like string theory, but it's definitely a challenge.
What other theoretical issues are there? You mentioned something about energy scales.
Right. There's a debate often framed as chaotic versus small field inflation. In some popular models, like Lind's chaotic inflation, the inflaton field doesn't start near the minimum of its potential, but can start way up high, with values potentially larger than the Planck energy scale.
The Planck scale, that's where quantum gravity effects become important, right?
Yeah, exactly. So if the inflaton field takes on these super Planckian values, it raises serious questions about whether we can trust the calculations based on standard quantum field theory in curved spacetime. Our theories might break down. These are called large field models.
And the alternative?
Small field models try to keep the inflaton field values below the Planck scale throughout inflation. But these models often tend to require even more severe fine-tuning of the potential shape to get enough inflation. So there's a tension there.
And the source mentioned a hierarchy problem connection.
Yeah, it's related. The energy scale associated with inflation, inferred from the CMB fluctuation amplitude, if it isn't too small, is around 1016 G. That's huge, but it's still significantly lower than the fundamental Planck scale of about 1019 GeV. Why this gap? It echoes the hierarchy problem in particle physics. Why is the electroweak scale so much lower than the Planck scale? Some see it as another potential fine-tuning issue for inflation, although others point out that 1016 GeV is intriguingly close to the scale where grand unified theories suggest the forces might unify, which could be a hint.
Okay, these are significant theoretical concerns, but let's get to what sounds like the most philosophically challenging and controversial aspect: eternal inflation and the multiverse.
Right. This is where inflation potentially leads to some really profound and deeply debated consequences. The issue arises because quantum fluctuations don't just affect the density, they can also affect the inflaton field itself as it rolls. In some regions of space, a quantum fluctuation might randomly kick the inflaton field back up the potential hill, overriding its slow roll downwards. If that happens, inflation in that region won't end. It will continue, perhaps indefinitely.
So inflation could restart itself in patches?
Effectively, yes. And because inflating regions expand exponentially, while regions where inflation has ended, like our observable universe, expand much slower, the total volume of the inflating regions grows much, much faster. It can come to dominate the total volume of the universe over time.
Leading to
a picture called eternal inflation, where the universe as a whole is constantly inflating, but dotted with pocket universes or bubble universes where inflation has ended locally, creating regions like the one we inhabit. The overall structure becomes this infinite fractal-like multiverse where new universes are constantly budding off from inflating space.
An infinite multiverse generated by inflation. That sounds wild. Why is this so controversial?
The core problem is often called the measure problem. If eternal inflation produces infinitely many pocket universes, potentially with different properties or outcomes of physical processes, how can we make any testable predictions? In an infinite set, anything that can happen will happen infinitely many times. So how do you calculate the probability of observing, say, the specific value of the cosmological constant or the mass of the electron that we see in our universe?
If everything happens infinitely often, probability seems meaningless.
Exactly. Standard probability theory breaks down. You can get different answers depending on how you choose to regulate the infinities or count the universes. This leads to paradoxes, like calculations suggesting we should be incredibly unlikely observers, or that inflation should almost never end from any observer's perspective. It seems to undermine the predictive power of the theory.
So it makes inflation potentially untestable.
That's the sharp criticism from people like Paul Steinhardt, who, remember, was one of the architects of new inflation. He and others argue that the multiverse is a disaster for inflation, making it fundamentally untestable and therefore unscientific in the Popperian sense. They argue it's more of a philosophical framework than a predictive theory. They've even make arguments, citing Roger Penrose's work on entropy, suggesting that getting our observed flat universe without inflation might be statistically far, far more likely than getting it with inflation once you consider the complexities and potential fine-tunings needed for the inflaton and the issues raised by eternal inflation.
Wow. Penrose himself has been a vocal critic too, right? Calling inflation falsified.
He has, yes, though often referencing specific observational claims like the initial BICEP2 results, which were later retracted. But his core argument relates to the initial entropy conditions required for inflation, which he argues are even more special, more fine-tuned than those needed for a standard Big Bang without inflation.
And what do the proponents like Guth and Lind say about the multiverse problem?
They tend to argue that eternal inflation is an almost unavoidable consequence of combining quantum mechanics with inflationary dynamics in many models. They believe we need to develop new mathematical tools or principles, new ways of defining probabilities or weighting observers, like anthropic reasoning, to handle the multiverse. They argue that just because it's hard doesn't mean it's wrong, and that the successes of inflation in explaining observations still stand. The debate is very much ongoing.
Let's quickly revisit the initial conditions problem. Did inflation really solve it, or just push it back to the pre-inflationary era or the inflaton's properties?
That's a fair question and part of the ongoing discussion. Some eternal inflation models try to evade the question by suggesting the multiverse has no beginning. It's always been inflating. Others connect inflation to ideas from quantum cosmology, like the Hartle-Hawking no-boundary proposal, attempting to show how an inflating universe might arise naturally from a quantum fluctuation from nothing.
Alan Guth called inflation the ultimate free lunch, right? Making universes seemingly out of inflating energy.
He did frame it that way. But critics like Don Page have pushed back, pointing out that while inflation creates matter and energy during reheating, it does so by converting the inflatant's potential energy. And crucially, the reheating process dramatically increases the entropy disorder of the universe. This implies that the state before inflation must have been even lower in entropy, even more ordered than the already low entropy state required for the standard Big Bang.
So it might make the initial entropy problem worse, not better.
That's Page's argument, potentially aggravating the puzzle of the universe's initial low entropy and the origin of the arrow of time. Others, like Albrecht and Sorbo, have countered that the total amount of non-gravitational energy required to start inflation might be much less than needed for a standard hot Big Bang, possibly outweighing the entropy concern. It's complex and ties into deep questions about gravity and entropy.
And one last theoretical issue mentioned was the Transplanckian problem.
Right. This is the concern that the physical length scales of the quantum fluctuations that eventually grew into galaxies and clusters we see today were actually smaller than the Planck length, the scale where quantum gravity must be important, before inflation stretched them out.
So they started in a regime where we don't know the physics?
Exactly. It raises the question.
Yeah.
Could unknown physics at the Planck scale significantly alter the predictions of inflation, which are usually calculated assuming standard quantum field theory holds even at those tiny scales? Some argue the effects should be negligible. Others think they could be observable or could undermine the calculations. It highlights our ignorance about physics at the ultimate unification scale.
Okay, so alongside the observational successes, there's a whole host of deep, challenging theoretical questions surrounding fine-tuning, quantum gravity effects, and the profound, maybe even troubling implications of eternal inflation and the multiverse.
That's a very good summary of the current theoretical status. It's a theory that works remarkably well in explaining observations, but it pushes us right to the edge of fundamental physics and raises questions that might even border on metaphysics.
Given these challenges, are there any serious alternatives to inflation being explored? Other ways to explain the flatness, horizon, and structure problems?
Yes, absolutely. While inflation is definitely the dominant paradigm, researchers are actively exploring alternative scenarios.
Can you give us a couple of examples?
One class of alternatives involves a big bounce instead of a Big Bang singularity. The idea is that the universe might have been contracting before expanding, reaching a point of minimum size and maximum density, and then bouncing into the expansion phase we see.
How would a bounce solve the problems?
Some bouncing models, perhaps involving modifications to gravity at high densities, like theories with torsion, claim they can naturally solve the flatness and horizon problems during the contracting phase or the bounce itself, without needing a separate period of inflation or an inflaton field.
Interesting. What else?
There are also ekpyrotic and cyclic models. These often involve ideas from string theory, like extra dimensions and colliding branes. In some versions, our universe undergoes cycles of expansion, contraction, a big crunch, and then a bounce or transition into a new phase of expansion, a hot Big Bang.
So the Big Bang wasn't the absolute beginning?
In these models, no. The horizon problem can be solved because there's a long period of slow expansion or contraction before the hot Big Bang phase, allowing regions to come into causal contact. They might avoid the monopole problem if the temperature never gets high enough during the bounce. Key challenges are ensuring they produce the right kind of density fluctuations, the n is 0.968, and making the bounce or transition work reliably without running into singularity problems.
Are there others? The source mentioned string gas cosmology.
Yes. That's another idea rooted in string theory. It treats the very early universe as a hot gas of fundamental strings. There are arguments suggesting that due to stringy effects, only 3 spatial dimensions are likely to grow large, potentially explaining why we live in 3+1 dimensions. Whether it fully solves flatness and generates the right perturbations is still under an investigation. Sometimes it's combined with bouncing ideas.
And varying speed of light.
VSL theories propose that the speed of light itself might have been much higher in the very early universe. A much faster speed of light could allow distant regions to interact and homogenize, potentially solving the horizon problem without needing exponential expansion. These theories face their own challenges, like consistency with fundamental principles and making detailed predictions.
So there are alternatives out there, but inflation remains the frontrunner for now.
That's fair to say. Inflation has the most developed framework and strong observational support, particularly from the CMB measurements like ENDS. But the alternatives are important because they highlight that inflation isn't necessarily the only way to explain the data, and they push theorists to explore different possibilities, especially given inflation's own theoretical puzzles.
Right. We've mentioned criticisms throughout, especially from figures like Penrose and Steinhardt regarding fine-tuning and the multiverse. Were there other critiques highlighted in the source?
The source mentions an earlier review by John Ehrman and Jesus Mostrand back in 1999, who argued at that time that inflation hadn't really made sufficiently unique and confirmed predictions to be considered part of the standard core cosmological model. Of course, much more precise data, especially from WNAP and Planck confirming the ENDS prediction, has come in since then.
So the observational case is stronger now than it was then?
Definitely. But the core criticisms from people like Steinhardt persist. That the influent field and its required potential shade seem ad hoc, custom-built for the job, and that the multiverse consequence makes the theory problematic, maybe even less likely than alternatives, despite the Planck data. He and collaborators have argued that the Planck results actually make inflation less likely, putting the paradigm in trouble. Although this interpretation is strongly contested by inflation proponents like Guth, Lind, and others.
Who argue the opposite.
Yes, proponents like Guth, Kaiser, Nomura, and Lind maintain that the Planck data, especially the ENDS measurement, puts inflation on stronger footing than ever before. So the debate continues quite vigorously.
It's fascinating. We have this incredibly powerful theory, cosmic inflation. It elegantly solves these major puzzles about our universe's beginnings, the homogeneity, the flatness, the origin of structure, and it's supported by key observations, especially from the CMB.
Right. The successes are undeniable.
But it simultaneously introduces these profound new puzzles. What is the inflatune? Is the required fine-tuning a sign of deeper physics or just a necessary feature? And perhaps most significantly, do we live in just one universe, or are we adrift in an infinite, eternally inflating multiverse, a consequence that challenges the very nature of scientific testability?
It really pushes us to confront fundamental questions.
So here's something for you to mull over. Is cosmic inflation, despite its theoretical baggage, truly the only viable explanation for what we observe? Or could one of these alternatives, maybe a big bounce, maybe a cyclic universe, eventually provide a cleaner, less paradoxical account? What kind of future observation, perhaps detecting those primordial B modes or something completely unexpected, might finally tip the scales and give us a definitive answer about how our universe truly began?
That's the billion-dollar question, isn't it?
Indeed. That wraps up our deep dive into cosmic inflation.
We covered a lot of ground.
We really did. From that initial burst of exponential expansion through the big problems it aimed to solve, those missing monopolies, the surprising flatness, the confounding horizon problem, we looked at how it might work with the inflaton field, traced the history of the idea, examined the really compelling observational evidence, but also wrestled with those significant theoretical challenges and criticisms that keep cosmology so exciting.
Hopefully this conversation has given you a clearer, maybe deeper picture of this remarkable and still very much debated theory at the forefront of cosmology. It's a field where new data and new ideas are constantly refining our understanding.
Thanks so much for joining us for this deep dive. If your curiosity is piqued, there are many fantastic resources out there to explore the ongoing research and the passionate debates surrounding inflation and the origin of our universe.
Absolutely. Keep looking up.
Until next time.
Welcome to the Deep Dive. Today we're plunging headfirst into, well, a really fundamental topic, metabolism. We've been looking at this comprehensive material on what actually powers life, how organisms get energy, build themselves up, keep everything running.
That's right. And our goal here in this deep dive is to kind of unpack all that complexity. We want to highlight the core ideas and maybe reveal some of the amazing efficiency behind the chemistry that makes everything tick, from a tiny bacterium all the way up to, well, you.
So if you've ever, say, eaten a meal and wondered, okay, how does this become that? How does food turn into energy? Or how does your body build muscle? Or maybe even how some weird microbes survive on, like, chemicals, then this deep dive should be right up your alley. Let's get into it. Okay, so first things first, metabolism. The word itself, I read, comes from the Greek for change, right?
Exactly, and change is the perfect word. Metabolism is essentially the grand total of all the chemical reactions happening inside a living thing just to keep it alive. It's like a nonstop, incredibly busy chemical factory. And it's got some really crucial jobs. Number one, take the energy that's locked up in food and convert it into a form cells can actually use. Number two, turn that food into the basic building blocks needed for, proteins, DNA, cell parts. And number three, just as vital, getting rid of all the waste products generated along the way.
So energy, building, and cleanup, all run by chemical reactions.
Precisely. And these aren't just random reactions happening willy-nilly. Oh, no. Every single step is incredibly precise, sped up, and controlled by these specialized protein molecules called enzymes. Without enzymes, things like growth, reproduction, just maintaining your structure, reacting to the environment, none of it could happen efficiently. And sometimes people use metabolism really broadly, including digestion and stuff. But often, when scientists talk about the core reactions happening inside the cells, they call that intermediary metabolism.
Okay, so within this huge web of reactions, is there like a fundamental split? You mentioned breaking down and building up earlier.
There absolutely is. That's the main division. Catabolism versus anabolism. Think of catabolism as the demolition phase. It takes big, complex molecules like the carbs or fats in your food and breaks them down into smaller, simpler pieces. And this process typically releases energy, breaking down glucose for energy, classic catabolism. Then anabolism is the construction phase. It uses those smaller pieces plus the energy captured from catabolism to build the complex molecules the cell needs, making new proteins, constructing cell membranes, storing energy for later. That's all anabolism. And these processes generally consume energy.
Okay. So catabolism kind of pays the bills and provides the bricks for anabolism to do the building.
That's a perfect way to think about it, yeah. And these reactions, they're not just isolated events. They're organized into these really elegant sequences called metabolic pathways. It's like an assembly line where a molecule gets passed along step by step with a different enzyme doing its specific job at each stage. This organization is key for, control and efficiency.
You mentioned building blocks. The source material talks about some key types of molecules that are central to all this, right?
Yes, absolutely. Life, at its core, relies on a surprisingly small set of basic molecular types. You've got your amino acids, carbohydrates, nucleic acids, and lipids, fats and oils. These are sort of the fundamental currency in the raw materials. Organisms either use them to build their own structures, their cells and tissues, or they break them down, catabolize them for energy. And these basic units can link together, like Lego bricks, to form much larger, complex structures called polymers. So amino acids chain up to make proteins, simple sugars, linked to form complex carbs like starch or cellulose. You get the idea.
Right. But with all these reactions, you need a way to move things around, like energy or specific chemical bits. Is that where coenzymes fit in?
Exactly. Enzymes are the catalysts, the workers, but coenzymes are kind of like the specialized delivery trucks or shuttles. They're intermediate molecules that pick up a specific chemical group, or maybe electrons, from one reaction and carry it over to another.
Yes.
They're constantly being used up and then regenerated, recycled. And the absolute superstar, the universal energy currency for pretty much all life we know, is adenosine triphosphate, ATP.
Yeah, everyone's heard of that one. What makes it so central?
Well, ATP is the molecule that directly hands over energy to make things happen in the cell, powering muscle contraction, building molecules, pumping ions. And what's truly mind-blowing is the sheer scale of its use. You don't actually store huge amounts of ATP, but it's recycled at an incredible rate. A human body, get this, probably uses and regenerates something like its own body weight worth of ATP every single day.
Wow. Its own weight every day.
every day. It just shows the constant, furious pace of activity happening inside our cells. ATP is that crucial link. Catabolism makes it. Anabolism spends it. It mainly works by transferring one of its phosphate groups onto another molecule, kind of like priming it with energy.
Okay, hold on. This makes something click from the source material vitamins. It says vitamins act as precursors for coenzymes. Is that why they're essential? Because they help build these shuttle molecules?
Bingo! You got it. That's exactly why. Many vitamins, particularly the B vitamins, are converted in our bodies into essential parts of these coenzymes. For instance, NAD+ and NADH, which are absolutely critical electron carriers in energy-releasing pathways, are derived from niacin, which is vitamin B3. And similarly, there are related ones like NADP+ and NADPH. They're also shuttles, but they're primarily involved in carrying the energy and electrons needed for the building up processes for anabolism.
So we have the organic molecules, the coenzymes?
Yeah.
But the sources also stress the need for simple inorganic stuff like minerals.
Oh, absolutely critical. Can't function without them. The ones we need in larger amounts, sodium, potassium, calcium, chloride, magnesium, these are key electrolytes. They're crucial for maintaining the right water balance, keeping pH stable, and they're fundamental for things like nerve impulses and muscle contractions, an action potential in a nerve. That's all about these electrolytes moving across membranes. And then you have the trace metals, needed in tiny amounts, like zinc, iron, copper, manganese. They often don't provide energy directly, but they act as essential helpers for enzymes. They bind to the enzyme, become a cofactor, and are often right at the heart of the chemical reaction the enzyme performs. Many enzymes simply wouldn't work without their specific metal partner.
Okay, let's dive back into catabolism, breaking stuff down. How do organisms, especially animals like us, actually extract energy from, say, a sandwich?
Right. The main goals are getting energy, usually as ATP, and getting those smaller building blocks for later use. How organisms do this varies wildly. There are microbes out there that live off things we find completely bizarre, like hydrogen sulfide gas using chemical energy sources totally unavailable to us. They're often categorized by where they get their energy in carbon. But for animals, breaking down food typically happens in 3 major stages. Stage 1 is basically digestion. Big molecules, proteins, complex carbs, fats get broken down into smaller units outside the cells, usually in the gut. Specialized enzymes are secreted to do this chopping up. Microbes often secrete enzymes into their environment to do something similar. Stage 2. Those smaller molecules, amino acids, simple sugars, fatty acids, are absorbed into the cells. Once inside, they get converted into an even smaller, really central molecule called acetylcoenzyme A or acetyl-CoA. This step releases a little bit of energy, but not the main payoff. Stage 3 is where the big energy harvest happens. That acetyl-CoA enters a pathway called the citric acid cycle, also known as the Krebs cycle. Here, the acetyl group is completely oxidized, broken down. This process generates electron carriers like NADH and releases CO2. Then, those electron carriers feed into the electron transport chain, which uses oxygen and ultimately produces loads of ATP. Water is also formed as a byproduct.
So that's the main highway. How do the different types of food, carbs, fats, proteins merge onto it?
Good question. They each have their own sort of on-ramp, but they mostly converge on that central acetyl-CoA molecule and the later stages. Carbohydrates, once they're broken down to simple sugars like glucose, mostly enter a pathway called glycolysis. It's a sequence of about 10 reactions that splits glucose into a molecule called pyruvate. This generates a bit of ATP and some NADH directly. Then usually pyruvate gets converted into acetyl-CoA to enter the citric acid cycle. But here's a neat twist. If oxygen is limited, like during really intense exercise, pyruvate doesn't become acetyl-CoA. Instead, it can be converted to lactate. This doesn't yield much energy, but crucially, it recycles NAD plus pyruvate, which is needed for glycolysis to continue. It's a way to squeeze out some energy from glucose anaerobically without oxygen. Fats, well, they're first broken into glycerol and fatty acids. Glycerol can hop into the glycolysis pathway. Fatty acids are chopped up 2 carbons at a time in a process called beta oxidation. Each 2-carbon chunk becomes acetyl-CoA. And this process, beta oxidation, releases a lot more energy per gram compared to carbs. That's why fat is such a good way to store energy. And amino acids from proteins. They're versatile. The cell prefers to use them for building new proteins. But if there's an excess, or if energy is really needed, they can be used as fuel. First, the nitrogen part, the amino group, is removed. This often gets processed through the urea cycle in mammals to safely dispose of the nitrogen. The remaining carbon skeleton can then be converted into various intermediates, some of which feed directly into the citric acid cycle, or some can even be used to make glucose.
Okay, let's really zoom in on the final stage, stage 3. Oxidative phosphorylation. You said it makes most of the ATP. How does that electron transport chain actually capture the energy? It sounds complex.
It is pretty amazing. Oxidative phosphorylation happens in specialized compartments, the mitochondria in our cells. It's where the vast majority of the ATP from glucose or fats is made. So you have these electron carriers, mainly NADH, that were loaded up with high-energy electrons during the breakdown of food. They deliver these electrons to the first complex in the electron transport chain, which is a series of protein complexes embedded in the mitochondrial inner membrane. The electrons are then passed along this chain, kind of like a bucket brigade, from one protein complex to the next. As they move down the chain, they drop in energy level. Now, the energy released as the electrons move isn't directly used to make ATP. Instead, several of these protein complexes use that energy to actively pump protons, hydrogen ions, from the inside of the mitochondrion to the space between its inner and outer membranes. This pumping action creates a steep concentration gradient of protons, like building up water pressure behind a dam. There's potential energy stored in that gradient. The only way for those protons to flow back down their gradient back inside is through a specific channel. And that channel is part of an incredible molecular machine called ATP synthase. It literally acts like a turbine, a biological rotary motor. As protons flow through it, they cause part of the enzyme to spin, and this mechanical spinning motion provides the energy to force ADP and phosphate together, synthesizing ATP.
A tiny spinning motor making energy in our cells. That's...
Wow. It really is one of nature's most elegant nanomachines. And remember, it's not just sugars and fats that can power this. Some microbes, the chemolithotrophs, they oxidize inorganic stuff like sulfur, iron, even ammonia, and funnel electrons from those reactions into similar electron transport chains to make their ATP. They're crucial for nutrient cycling in ecosystems. And of course, you have the phototrophs, plants, algae, some bacteria capturing energy from sunlight, photosynthesis. They also use electron transport chains driven by light energy to create a proton gradient across a membrane. Then ATP synthase uses that gradient to make ATP. That's called photophosphorylation. Plants use that ATP, plus reducing power in the form of NADPH, also generated using light, to fix CO2 into sugars.
Okay, so we've covered the power generation, the catabolism. Now, what about the other side, anabolism? Using that energy to actually build things.
Right, the construction phase. Anabolism is all about synthesizing the complex molecules the cell needs: proteins, DNA, RNA, lipids, polysaccharides from smaller, simpler precursors. And this requires energy primarily from ATP and often reducing power, typically from NADPH, which were generated during catabolism or in phototrophs from light capture. It generally happens in 3 stages too, conceptually. First, you need the basic precursors: amino acids, simple sugars, fatty acids, nucleotides. Organisms either make these themselves or get them from their diet. Second, these precursors often need to be activated, usually by attaching them to something using energy from ATP. Third, these activated precursors are assembled into the final complex molecules linking amino acids into proteins, sugars into starch, and so on. And how much building an organism has to do from scratch really varies. You have autotrophs, like plants, which are master builders. They can synthesize almost everything they need from very simple inorganic materials like CO2, water, and minerals using light or chemical energy. Then you have heterotrophs, like us animals, fungi, or more like assemblers. We need to get many of the essential building blocks, like certain amino acids and fatty acids, ready-made from our food.
Carbon fixation, pulling CO2 out of the air to make organic stuff that seems like the ultimate starting point for so much of life's building projects.
It really is, especially for the photoautotrophs, the organisms running photosynthesis. They use sunlight energy, captured as ATP and NADPH during the late reactions, to power the dark reactions, or more accurately, the Calvin-Benson cycle. This cycle takes CO2 from the atmosphere and, using a key enzyme called rubisco, probably the most abundant protein on the planet, incorporates that carbon into organic molecules, eventually producing sugar precursors. Plants have evolved some clever variations on this, like C4 and CAM photosynthesis, which are adaptations to help them capture CO2 more efficiently, especially in hot, dry conditions where they risk losing too much water. And prokaryotes, they have an even wider, frankly amazing diversity of ways to fix carbon dioxide using various energy sources.
Okay, what about building other major components? Complex carbs, fats?
Right. Complex carbohydrates, also called glycans or polysaccharides, are built up from simple sugar units. Often, glucose is the starting point. If glucose isn't available, many organisms can make it from other precursors like pyruvate or certain amino acids via a process called gluconeogenesis, literally new glucose creation. And importantly, this isn't just glycolysis running in reverse. Key steps are catalyzed by different enzymes, allowing the cell to regulate glucose breakdown and synthesis independently. And an interesting point from the source: vertebrates, like us, cannot convert fatty acids back into glucose. We lack a key pathway, the glyoxylate cycle, that plants and bacteria have, which lets them do this. So during fasting, we rely heavily on making glucose from amino acids or lactate. Once glucose is made or obtained, it can be stored, typically as glycogen in animals, through a process called glycogenesis. Polysaccharides are built by adding sugar units one by one, sometimes creating branch structures like glycogen or starch. Fatty acids themselves are synthesized typically by joining together two carbon units derived from acetyl-CoA, using large enzyme complexes called fatty acid syntheses. Animals and fungi tend to have one type, plants and bacteria another. Other lipids, like terpenes and steroids, including cholesterol, are built from repeating 5 carbon units called isoprenes, assembled through different, quite complex pathways.
It's just incredible how interconnected and, well, organized it all seems.
Yeah.
But what happens when the cell runs into stuff it doesn't normally encounter? Like, say, drugs or environmental pollutants.
Yeah, that's the challenge of xenobiotics. That's the term for foreign compounds, things like synthetic drugs, pesticides, industrial chemicals, even some natural toxins that aren't part of the organism's normal diet. If these build up, they can be really harmful. So organisms have evolved detoxification systems. In humans and other animals, this often involves a set of enzymes, particularly the cytochrome P450 family. These enzymes chemically modify the xenobiotic, often adding oxygen atoms, phase 1. Then other enzymes attach water-soluble groups like sugars or glutathione, phase 2, making the compound easier to eliminate from the body, usually via urine or bile, phase 3. Microbes, especially bacteria, are often metabolic wizards in this area, capable of breaking down an astonishing range of compounds, which is crucial for bioremediation of polluted environments. Another constant battle is oxidative stress. Just using oxygen for energy production, especially in that electron transport chain, inevitably generates some nasty side products, reactive oxygen species like hydrogen peroxide. These guys can damage DNA, proteins, lipids, so cells have elaborate antioxidant defenses. These include small molecules like glutathione or vitamin C and E, and specialized enzymes like catalase and superoxide dismutase that neutralize these reactive species before they cause too much damage.
All this breaking down, building up, dealing with toxins. It must all operate within the fundamental laws of physics, right? Thermodynamics comes to mind.
Absolutely. You can't escape thermodynamics. Living organisms are what physicists call open systems. We exchange energy and matter with our environment. And while we create and maintain this incredible internal order and complexity, we do so by increasing the disorder, the entropy of our surroundings, primarily by releasing heat. Metabolism is precisely how life pulls this off. It cleverly couples energy-releasing reactions, catabolism, which happens spontaneously, to energy-requiring reactions, anabolism, which wouldn't happen on their own. It's a constant flow and transformation of energy that maintains local order at the expense of greater disorder elsewhere, perfectly consistent with the second law of thermodynamics. And because conditions change food availability, temperature, signals from other cells, metabolism has to be incredibly tightly regulated. This allows the organism to maintain a stable internal environment, homeostasis, and respond effectively to changes.
So how does that regulation actually work?
It happens on multiple levels. Some regulation is intrinsic to the pathways themselves. For instance, the end product of a pathway might inhibit one of the first enzymes in that same pathway. That's feedback inhibition. Often this involves allosteric enzymes, where the inhibitor binds to a site different from the active site, changing the enzyme's shape and slowing it down. Then there's extrinsic regulation, where the cell responds to external signals, hormones like insulin or adrenaline growth factors. These signals bind to receptors on the cell surface and trigger internal signaling cascades. These cascades often involve adding or removing phosphate groups from key metabolic enzymes, effectively flipping switches to turn pathways on or off.
Like the insulin example you mentioned earlier, controlling glucose.
Exactly. Insulin binding to its receptor triggers a cascade that ultimately leads to cells taking up more glucose from the blood and activating enzymes that convert that glucose into storage forms, like glycogen or fat, while simultaneously inactivating enzymes that would break down glycogen or make new glucose. It's a beautifully coordinated response, ensuring the body handles fuel appropriately based on the current situation.
Thinking about how pathways like glycolysis seem to be almost universal, it really makes you wonder about the history. How did this incredible metabolic network evolve in the first place?
That's a huge and fascinating question. What's really striking is that many of the central metabolic pathways, glycolysis, the citric acid cycle, pathways for making amino acids and nucleotides, are found across all known domains of life: bacteria, archaea, and eukaryotes like us. This strongly suggests they were present in the last universal common ancestor, LUCA, billions of years ago. They're likely retained because they're just fundamentally efficient ways to manage energy and carbon. How they arose is debated. Ideas include the gradual step-by-step addition of new reactions to existing simpler pathways, or perhaps enzymes being duplicated and then evolving slightly different functions, or even whole pathways being recruited for new purposes. It seems likely it was a combination of these things, maybe like building with molecular Lego blocks that get reused and rearranged over time. And evolution works both ways. Sometimes organisms lose metabolic capabilities. Parasites, for example, often shed the pathways for making things they can just steal from their host. Or organisms living in very stable, nutrient-rich environments might lose pathways they don't need anymore.
It seems almost impossibly complex. How do scientists even figure all this out? How do you study metabolism?
Yeah, it's a massive puzzle. Historically, a lot of it was painstaking work, isolating individual enzymes, figuring out what reaction they catalyzed, using radioactive isotopes as tracers to follow specific atoms through a pathway. Like feeding an organism glucose with labeled carbon atoms and seeing where those labeled carbons ended up. More recently, we have powerful omics technologies. Metabolomics aims to identify and quantify all the small molecules, the metabolites, in a cell or tissue at a given time, giving a snapshot of metabolic activity. Genomics tells us all the genes an organism has, many of which code for metabolic enzymes. And crucially, we now use computational approaches. We can take the genomic data and reconstruct an organism's entire potential metabolic network. Then we can build mathematical models based on these networks to simulate metabolic behavior, predict how the cell might respond to changes, or identify bottlenecks. This network view is really powerful, even for understanding human disease. Researchers are building detailed models of human metabolism to see how diseases like cancer or diabetes disrupt the network and how different parts of the network are interconnected. And this knowledge allows for metabolic engineering. That's where scientists deliberately modify the metabolism of microbes like yeast or bacteria to get them to produce useful things, maybe antibiotics, biofuels, industrial chemicals more efficiently, or even to make novel compounds.
It's clearly a modern field, but it sounds like it has some deep historical roots, too.
Oh, absolutely. The quest to understand metabolism goes way back. You mentioned Santorio in the early 1600s with his weighing chair experiments. That was remarkably early quantitative biology, showing that something invisible was being lost, what he called insensible perspiration, part of which we now know is CO2 and water vapor from metabolism. A huge moment was in 1828 when Friedrich Wöhler synthesized urea, an organic waste product from inorganic chemicals. This shattered the idea of vitalism, the belief that organic molecules possess some mystical life force and couldn't be made in the lab. It showed the chemistry of life followed the same rules as non-living chemistry. Then, in the 19th century, Louis Pasteur's work on fermentation was key. He demonstrated that fermentation wasn't just spontaneous decay, but was carried out by living microorganisms, by their internal ferments. Later, Edward Buchner took it a step further around 1900. He showed that even a cell-free extract of yeast could still carry out fermentation. This proved the ferments were chemicals enzymes launching biochemistry as a distinct field. And you can't talk about metabolism history without mentioning Sir Hans Krebs. His work in the mid-20th century was monumental, figuring out the urea cycle and, of course, the citric acid cycle, that central hub of energy metabolism, often just called the Krebs cycle in his honor. Modern tools just keep revealing more layers of this incredible complexity.
Wow, what an absolutely incredible journey through the intricate machinery of metabolism. From tiny chemical handoffs to the grand scale of powering and building life itself.
It really does show you how interconnected everything is, doesn't it? And how these fundamental chemical strategies are conserved across basically all life we know. It's quite humbling, really.
Just thinking about these millions, billions of reactions happening right now in every one of our cells, constantly adjusting. It's kind of mind-bending.
It is, that exquisite regulation, the constant dynamic balance between breaking down and building up. That is the engine of life, running constantly.
So maybe you should go about your day today. Just pause for a second and think about that incredible ancient chemical symphony playing out inside you, powering every breath, every thought. And perhaps ponder this. How did these fundamental chemical tricks, evolved billions of years ago, become the basis for the absolutely staggering diversity of life we see all around us? Something to chew on. Thanks for taking this deep dive into the chemistry of life with us. All right, let's unpack this. You've handed us a truly fascinating stack of material, and today we are doing a deep dive into one of the world's most unique places, Vatican City.
It's incredible when you really look at it. Less than half a square kilometer, right?
Yeah, tiny.
Nestled right in the heart of Rome, yet it's somehow a sovereign state, a city, and the global headquarters of a major institution all wrapped into one.
Exactly. And our mission with these sources today, to explore the history, how it even came to be, the utterly unique way it's governed, some truly quirky facts you won't find anywhere else, and maybe pull out some surprising insights hidden within its walls.
Yeah, should be interesting.
Get ready for some aha moments, I think, as we navigate this tiny territory with, well, immense global reach.
What's fascinating right from the start is that while Vatican City State, the independent country we know today, is actually relatively young.
Right, 1929.
Established in 1929, exactly.
Yeah.
But the story of the area itself and the whole, that goes back, well, centuries.
Yeah.
Millennia, really.
Millennia. The name itself, Vatican Hill. The sources say it was an Etruscan area. Ager Vaticanus.
That's right. Before Rome was even fully established as we think of it.
And it wasn't exactly prime real estate back then, was it?
No, not at all. Marshy apparently considered a bit ominous by the ancient Romans.
And poor quality wine, the sources mention.
Definitely a far cry from its modern image. But then its destiny started to change. First, you had Emperor Caligula and Nero. They built their circus there.
The circus guy ate Neronis.
Right. And then, crucially, tradition places the martyrdom of St. Peter in that very location, or very nearby.
Okay, here's where it gets really interesting then. Because that spot, believed to be Peter's tomb, which was in an existing cemetery, that became the foundation for the first huge basilica, the Constantinian one, built way back in 326 AD.
And that really anchored the site. From there, over centuries, things grew. A papal palace was eventually built nearby, and the popes started wielding not just spiritual power, but, secular power too.
Ruling the papal states, right. That much larger territory across central Italy.
For over 1,000 years, yeah. But interestingly, their main home wasn't always the Vatican itself. For a long time, the main papal residence was the Lateran Palace across town in Rome. And of course, there was that whole period in the 14th century when the papacy was based in Avignon, France.
Right, the Avignon papacy.
Yeah.
So the Vatican site was important, certainly, but not the only center of power.
Exactly. The big modern turning point really comes in the mid-19th century with the unification of Italy.
The Risorgimento.
Yes. And by 1870, Italian forces had taken over all the papal states, including Rome itself, making it the capital of the new Kingdom of Italy.
Which led to the Roman question.
Precisely. This period from 1870 all the way up to 1929. With Rome now Italy's capital, the popes basically withdrew behind the Vatican walls. They saw themselves, and were often described as prisoners in the Vatican.
Wow. Nearly 60 years of that uncertain status.
A very long time. And that situation is finally resolved with the Lateran Treaty, February 11th, 1929.
Signed by Mussolini for Italy and Cardinal Gaspari for the Holy See.
Correct. And the sources are really clear on this point. This wasn't about giving back the old papal states. No.
Yeah.
It was the creation of something entirely new. The independent state of Vatican City, a tiny territory to guarantee the Pope's independence.
And that independent status, that neutrality, became absolutely critical during World War II.
Hugely important. The Holy See, under Pope Pius XII, officially pursued neutrality, but it was a very delicate situation.
I can imagine. Rome was occupied by German troops after Italy switched sides in '43.
Right. And the sources mention incidents like protests near the Vatican when the British dropped propaganda leaflets and Allied bombs hitting the railway yards very close to the Vatican walls, targeting Axis supply lines.
But generally, its neutrality was respected.
Largely, yes. Both sides, despite some tense moments and accusations, generally respected the Vatican's neutral territory. It really showed the significance of that 1929 treaty.
Okay, so post-war, what changes?
Well, there's continued evolution. Most of the old papal military units like the Palatine Guard and Noble Guard were disbanded in 1970.
Leaving just the Swiss Guard.
Just the Swiss Guard. Then there was a new agreement, a concordat, with Italy in 1984. It modified some aspects of the Lateran Treaty, like Catholicism no longer being the official state religion of Italy.
Interesting. And the sources even mentioned, a dispute over a building blocking views?
Yeah, in 1995. almost mundane, but it shows the practicalities of being a tiny state bordered entirely by another country. There was a fuss about a new Vatican building casting shadows or blocking views for adjacent Italian apartments.
Huh. And there's even some modern debate noted in the sources, right, about whether its status as a sovereign state created by that treaty is sort of problematic in international law today.
Yes, there are legal scholars who discuss that, how its sovereignty derives from a treaty with just one other state initially, rather than emerging organically. It's a unique case.
Okay, so that history brings us to today. And you mentioned something crucial earlier, the difference between Vatican City State and the Holy See.
Absolutely fundamental. They are not the same thing. And the sources stress this distinction.
Right. So the Holy See is the older entity, the spiritual one.
Exactly. The Holy See is the ancient juridical entity representing the central government of the entire Catholic Church worldwide. It existed for almost 2 millennia before the Vatican City State was created.
And it maintained its international sovereignty even during that prisoner period when it had no territory.
That's the key. Its sovereignty is inherent to its nature as the head of the Church, recognized internationally long before 1929. The Vatican City State, created by the Lateran Treaty,
Yes.
provides the Holy See with a territorial base, a physical guarantee of independence. The sources call the state a significant but not essential instrument of the Holy See.
Ah, okay, so the state exists for the Holy See to give it that temporal independence.
Precisely. The Holy See is the main actor on the world stage. The state is its territorial support.
Okay, that clarifies a lot. So, given that unique purpose, how is this tiny state actually governed? The description is quite something. A unitary, theocratic, Catholic, elective, absolute monarchy.
It is quite a mouthful, and it's accurate. The Pope, because he's the Bishop of Rome and head of the Church, is automatically the sovereign of Vatican City State. He's the head of state.
And absolute monarchy means literally absolute.
Yes. The sources confirm he holds supreme legislative, executive, and judicial power within the state. It makes him, as the sources point out, the only remaining absolute monarch in Europe.
Wow. But obviously he delegates day-to-day running.
Of course. Legislative authority for the state is delegated to a pontifical commission, usually made up of cardinals, appointed for 5-year terms.
Okay.
And executive power is delegated to the president of the governor of Vatican City State. The current president, interestingly, as the sources note, is Sister Raffaella Petrini.
A woman holding that key executive role, that's significant.
It is. And the governance structure gets particularly interesting during a seat of icon, the period between popes.
Right, when the seat is vacant, what happens then?
The administration falls primarily to the Cardinal Camerlengo, currently Cardinal Kevin Farrell, along with 3 assistant cardinals chosen by lot. They handle the ordinary affairs of the Holy See and, sort of by extension, the basic functions of the Vatican State.
But their power is limited.
Strictly limited, the sources emphasize they can't make major decisions or change policy. Their role is essentially caretaker, keeping things running smoothly until a new pope is elected and takes charge again.
Got it. And the judicial system.
There are specific courts: a Supreme Court, a Court of Appeal, a tribunal, and a sole judge for minor cases.
And I found that detail fascinating. If someone is convicted of a crime there, where do they serve their sentence?
Often in Italian prisons, there's an agreement where Italy handles incarceration and the Vatican covers the costs. It's another example of that practical interdependence.
Okay, let's shift to the people living there. The population is minuscule, right?
Incredibly small. The sources cite just 882 residents actually living within the walls in 2024. Maybe a few hundred more citizens living abroad for work, like diplomats.
And citizenship. This is probably the most unusual aspect. It's not about birth or bloodline.
Not at all. No, just soli, right of soil, or just sanguinis, right of blood. It's based on just officii, the right of office.
Meaning your citizenship comes with your job.
Essentially, yes. It's granted to those who hold specific offices or employment in service of the Holy See or the Vatican City State. And crucially, it usually ceases when that employment ends.
Wow. So it's temporary for many people.
For most lay people, yes. It can be extended to spouses and children, but only if they reside within the Vatican walls with the employee.
And what happens if you lose your job and thus your citizenship? Are you left stateless?
No, and this is important. The Lateran Treaty has a provision ensuring that anyone who loses Vatican citizenship and doesn't hold another nationality automatically becomes an Italian citizen.
Ah, Italy acts as a backstop. So the population makeup is really tied to the function of the place.
Entirely. It's mostly clergy, members of religious orders, lay officials, the Swiss Guard, and then the families of some of those lay workers.
And because it's so small and has this unique demographic profile, it leads to some really weird statistical anomalies.
Oh, absolutely. They really stand out in per capita figures. For instance, the gender ratio is heavily skewed male.
Because most of the roles conferring citizenship are traditionally held by men, like clergy and the Swiss Guard.
Exactly. And then there's the crime rate statistic.
Right, the one that makes headlines, sometimes a very high per capita crime rate.
Yes, but the sources are very careful to explain this. It's almost entirely petty crime pickpocketing, shoplifting directed at the millions of tourists who flock to St. Peter's Square each year.
Which is technically Vatican territory, but policed differently, as we'll get to.
Right, so the tiny resident population number divided by the huge number of tourist-related incidents creates this misleadingly high per capita rate. It doesn't reflect crime among residents.
That makes sense. It's a denominator issue. And my favorite quirky stat.
Let me guess. Wine consumption.
Yes. Leading the world in per capita wine consumption.
The sources attribute this mainly to its use in the Mass, the sacramental wine distributed to clergy and potentially staff, though I'm sure communal meals play a part too.
Yeah, it's not necessarily everyone drinking heavily every day. The sources also humorously mention calculating things like popes per square kilometer as another illustration of these anomalies.
It highlights how standard statistics just don't quite fit this unique place.
So how does a state this small, this unique, handle security and its place on the global stage?
Well, for military defense, the sources are clear. It relies on Italy.
Is there a formal treaty for that?
No formal defense treaty, mainly because Vatican City maintains official neutrality. But given it's entirely surrounded by Italy, Italy is its de facto protector.
Makes sense. The visible security force, though, the one everyone recognizes.
The Pontifical Swiss Guard. Iconic.
Their role is specifically protecting the Pope. Right. Personal bodyguards.
Yes, that's their primary mission. And the sources list those very specific recruitment criteria. Must be a Catholic, unmarried male, Swiss citizen, completed basic training in the Swiss Army, between 19 and 30 years old, and at least 174 centimeters tall.
Very specific. And they are technically a core of the Holy See, not the Vatican State.
Correct. But while serving, their soldiers do receive Vatican citizenship.
Okay, so who handles regular policing within the Vatican?
That's the Corps of Gendarmerie of Vatican City State. They're the state's police force.
What do they do?
Public order, border control, like the entrances to the Vatican, criminal investigations, traffic control, and they also provide security for the Pope when he travels outside the Vatican, coordinating with local police.
And St. Peter's Square. That's a special case, isn't it?
It is. Even though the Lateran Treaty defines it as Vatican territory, normally the responsibility for policing the crowds in the square falls to the Italian police.
Interesting overlap there. What about foreign relations, diplomacy?
That's almost entirely handled by the Holy See, not the Vatican City State as a state. The Holy See has one of the oldest and most extensive diplomatic networks in the world.
Relations with countries globally.
Yes, and many international organizations. But because Vatican City is so tiny...
There's no room for embassies.
Exactly. Foreign embassies accredited to the Holy See are physically located in Rome, in Italian territory.
And at the UN.
The Holy See has permanent observer status, which allows it to participate in debates and activities but not vote in the General Assembly. Vatican City State itself, the territory, is not a UN member.
But the state is a member of some international bodies?
Yes, usually ones related to its physical functioning as a territory. The sources list things like the Universal Postal Union, UPU, the International Telecommunication Union, ITU, Interpol.
Things a state needs to function practically.
Right. Things related to mail, phone signals, international police cooperation on specific issues.
Okay, but there's also this aspect of the Vatican sometimes standing apart from international agreements. The sources mention a non-party, non-signatory policy on some things.
Yes, that's significant. It's notably not a member of the International Criminal Court, ICC.
Or the Council of Europe.
Correct. And on the financial side, the sources point out it hasn't signed the OECD's Common Reporting Standard, CRS, which is about automatic exchange of tax information.
And this connects to past criticisms.
Yes. The Vatican, particularly the Vatican Bank, has faced significant criticism and scrutiny over the years regarding financial transparency and allegations of being used for money laundering in the past. Not signing on to some of these transparency initiatives is noted.
The sources also mention it's one of the few countries not providing public financial data to the IMF.
That's also noted, yes. It contributes to that image of financial opacity, although reforms have been underway.
So how does this unique place actually fund itself? What's the economy like?
It's unique, like everything else. A big part is donations, particularly Peter's Pence collections from Catholics worldwide, which go to the Holy See to fund its global mission and administration. That's separate from the state's budget.
Okay, so what funds the state itself, running the territory?
Revenue comes from admission fees to the incredibly popular Vatican museums. That's a major source.
Okay.
Also, sales of postage stamps, coins, metals collectors love Vatican issues, and souvenirs, publications.
Are there any industries inside the Vatican?
Small-scale ones, the sources mention, things like printing, producing mosaics, making clergy and Swiss Guard uniforms. And they note that lay workers employed by the Vatican generally earn wages comparable to similar jobs in Rome.
And the famous Vatican Bank, the IOR.
The Institute for Works of Religion handles financial activities. It's not exactly a typical bank, more of a financial institute for Vatican entities, religious orders, clergy, employees. And yes, the sources make a point of mentioning its ATMs.
With instructions in Latin.
Indeed. A nice touch of tradition.
Use of the euro now, right?
Yes. Through a special monetary agreement with the European Union, via Italy, they get to mint their own Vatican euro coins.
But very few of them.
Very limited quantities, which makes them highly prized by numismatists, by coin collectors.
The sources gave some budget numbers, showing fluctuations, surpluses sometimes, deficits others.
Yes, like a surplus in 2007, then a deficit in 2008 after the financial crisis hit donations and investments. It shows it's not immune to global economic trends.
And you mentioned reforms under Pope Francis.
Yes, the sources touch on that. He established a new Secretariat for the Economy to oversee finances, brought in international auditors, aiming for greater transparency and accountability, partly in response to those past scandals.
NFT plans. Really?
Apparently so. Plans to create non-fungible tokens of masterpieces from the Vatican museums. Talk about blending the ancient world with the latest tech trend.
Wow. Okay, transport.
Yeah.
Given the size, must be pretty limited.
Extremely. There's a heliport used by the Pope and visiting dignitaries, and the famous Vatican Railway.
The world's shortest national railway system.
That's the one. Just a couple of sidings and a station, mostly used for freight now, connecting to the Italian rail network just outside the walls. No airports, no highways within Vatican City.
Makes sense. But communications are modern.
Fully. It has its own telephone system, its own internet top-level domain, which is .va.
.va.
And its own media. Vatican Radio is historic, set up by Marconi himself in 1931, broadcasting in dozens of languages. There's also the Vatican Television Center, though these are really organs of the Holy See, now consolidated under the Dicastery for Communication.
And the Postal Service, post-Vatican, reputedly very efficient.
Yes. Established in 1929 along with the state, it has a reputation maybe partly legendary for being faster and more reliable than the Italian post next door. Lots of philatelists use it.
And physically, a huge chunk of the territory isn't buildings, right? It's gardens.
About half of it, yes. The Vatican gardens are extensive, dating back to medieval times, filled with fountains, sculptures, grottos, greenery. A really significant geographical and, you could say, cultural feature of the state.
Speaking of culture, this is where the Vatican's global impact is maybe most visible.
Undeniably. It's a UNESCO World Heritage Site, but uniquely, the listing covers the entire state.
The whole country is a World Heritage Site.
Yes. And it's also registered under the Hague Convention for protecting cultural property in wartime.
That just underscores its immense value. The sources obviously highlight the big names. St. Peter's Basilica.
Designed by giants like Bramante, Michelangelo, Maderno, Bernini, it's just breathtaking.
The Sistine Chapel.
With Michelangelo's ceiling and his Last Judgment on the altar wall, but also frescoes by Botticelli, Perugino, other Renaissance masters.
The Vatican museums, just packed with treasures.
Absolutely. And the Vatican Apostolic Library, holding priceless ancient manuscripts and books. These aren't just tourist sites. They're repositories of history, art, science, culture for the whole world.
But it's not just art and history, is it? The sources mention a significant scientific dimension, too.
Yes, which might surprise some people. The Pontifical Academy of Sciences, established in its current form in 1936, but with deeper roots.
What does it do?
It brings together top scientists from around the world, including many Nobel laureates, regardless of their religion, to discuss and advise on scientific issues. Covers maths, physics, natural sciences.
And there are other academies?
Yes, one for social sciences and one for life, which deals heavily with bioethics, shows an engagement with contemporary intellectual fields.
And the Vatican Observatory. That has a long history.
Very long, origins back in the 16th century with calendar reform. It continues astronomical research today.
But light pollution in Rome must be an issue.
Huge issue for the telescopes, actually, at the Vatican. So the sources note they have partnerships and operate the Vatican Advanced Technology Telescope, or VATT, in collaboration with the University of Arizona, located in rural Arizona where the skies are dark.
Smart solution. Keeping the tradition of church involvement in astronomy alive.
Exactly. And finally, the sources touch on something very current: sustainability efforts.
Inspired by Pope Francis's encyclical, Laudato Si'.
Very much so. There's a clear push towards environmental stewardship.
What kind of things are they doing?
Concrete initiatives. Expanding solar power, the roof of the Paul VI Audience Hall is covered in photovoltaic panels.
I've seen pictures of that.
Promoting electric vehicles within the Vatican, installing charging stations, aiming to replace the state's fleet. They banned single-use plastics back in 2019.
Ahead of many places.
Yes. Improving waste management and recycling, aiming for high rates, like 55% reported, and implementing energy efficiency measures in buildings. It shows a commitment to practicing what they preach on creation care, even within their unique small state.
So you see, when you really dive deep into these sources on Vatican City, it reveals so much more than just that tiny dot on the map of Rome.
Absolutely. It's incredibly complex, multi-layered. You've got this blend of ancient history, millennia-old institutions, bumping right up against very modern challenges and structures.
A temporal state, yes, but one existing purely to support a vast global spiritual mission.
And within that tiny space, you find unparalleled art, a system of governance that exists literally nowhere else on Earth.
And all those statistical quirks that just make you scratch your head until you understand the context.
It really leaves you with a fascinating question, doesn't it?
Which is,
how does a state like this, one whose entire reason for being is to guarantee the independence of a spiritual authority, how does it actually navigate the very secular, often messy world of international law, global finance, security alliances, even things like environmental standards?
While still holding on to its absolutely unique identity and mission.
Exactly. How does it balance being in the world, but perhaps not entirely of it in a practical state-level sense?
That is definitely something to ponder as you continue your own exploration of the world's unique corners.